Okay, so this is chapter 2, Essential Chemistry for Biology. So this is a little chemistry review. If you've had chemistry recently, this is going to be pretty simple. If it's been a while, or you've never had it, then you need to pay close attention. And we're going to just look at the basics of what are atoms made of, and what kind of bonds there are. And at the end of the chapter, we'll talk about water and the different properties of water and pH. So let's look at Roman number one, atoms and their interactions. So atoms are listed on the periodic table. An atom is a substance that cannot be broken down by chemical reactions anymore. So no natural chemical reaction can break these units down. So that is the most basic, fundamental building block we have. Atoms are, there are different kinds of atoms, and they're on the periodic table. So all these letters, all these abbreviations stand for a different kind of atom. And so we also use the word element because elements are, basically these are elemental units. So the elements all have a abbreviation. They all have different chemical properties. So we'll look at those. But we want to first talk about what are the parts of an atom. So let's look at our subatomic particles. And you're going to need to know these definitely for the test. And I have questions. Which has a charge? Which one has a charge, or what charge? Which one has mass? Which one does not have a mass? So let's look at the general setup of an atom. So there is a central portion here that has a very tightly clustered, very dense subatomic particles. There's the protons and neutrons found in the nucleus of the atom. And you can see that the protons have a positive charge here. So every proton has a positive charge of 1. There's 2 protons in this picture, so that's a charge of 2, positive 2. Neutrons are also found in the nucleus of an atom. Neutrons do not have a charge. That's the word neutral means that there's no charge. And then orbiting the nucleus, that's it for the nucleus. The nucleus just contains protons and neutrons. Orbiting the nucleus in a cloud, okay, so a lot of times we have these rings depicted around the nucleus, and that's just for sort of really easy, an easy way to draw the electrons orbiting the nucleus, but in fact it's more like a cloud, and these clouds have different shapes. But so just keep that in mind. They don't actually orbit in one line like you see in these pictures. The electrons that hover around the nucleus they're called orbital shells that they're hovering in, and they have a negative charge. So if there's 2 electrons in this shell, then that has a negative charge, negative 2 charge, right? So let's talk about mass. Protons and neutrons, the items in the nucleus, have a mass of 1. So protons weigh 1, neutrons weigh 1. The unit used here is atomic mass unit, so AMU, atomic mass unit. And electrons are so light and so small that their mass is negligible. So we basically say that electrons don't donate anything to the weight or the mass of an atom, so their mass is 0, okay? So if you wanted to know how much an atom weighed, what the mass of an atom is, you only look at the nucleus. And if you wanted to know the charge of an atom, you would have to look at the number of protons it has in the nucleus, and then how many electrons it has in the orbits. And if they're the same number, then it's a neutral atom, okay? Now, they can be different numbers. We'll look at that in just a bit. So for now, I just want you guys to know protons and neutrons in the nucleus, electrons orbiting the nucleus, and protons and neutrons have a mass of 1 atomic mass unit. Electrons do not have mass. And you also see protons have a positive charge and electrons have a negative charge. All right, so let's take a look at the atomic number and the atomic mass. So the atomic number is the number of protons an atom has. So let's actually look at the table one more time. This one highlights carbon. So carbon is abbreviated with the letter C. And this is the basic notation. So in the upper part of the box of the periodic table, you'll find a number, and that's the atomic number. So every single one has a different number. That number tells you how many protons it has. And this is really important. The number of protons an atom has tells you what the atom is. So anything out there with 6 protons in its nucleus is carbon, okay? If it loses a proton, and that's possible, a proton is lost, and then this number turns to 5, it's no longer carbon. Then you have to go step 1 back, and it's boron. If there's a gain of a proton, it's no longer carbon. It's number 7 then, it's nitrogen. Okay, so the number of protons dictates what that atom is. And then the bottom number is the weight or the mass. So the mass number, so remember the units, the subatomic particles in the nucleus give it the mass, right? So the mass is going to be the protons plus the neutrons. And remember that for most of the time, the number of protons is going to be the same as the number of neutrons. So let's go back to this picture here, right? We have 2 protons in the nucleus. That means we also have 2 neutrons in the nucleus. That's just assume they're the same, unless we're going to talk about isotopes, and that's going to be a little bit different. You should also assume that atoms are neutral. So if there are 2 protons in the nucleus, you will assume that there are 2 electrons in the orbital shell. Okay, so that number can change, and we'll talk about that. But for basically the standard start, we're going to do that. So atomic number is the number of protons, determines what element it is, right? What if a carbon lost a proton, right? I mentioned it was going to be boron. What if nitrogen gained a proton? Well, we need to look. Nitrogen is here. If it gained a proton, it's going to go up 1 number. It's oxygen. So this periodic table is really simple. It doesn't have any numbers. I'll show you another periodic table. This periodic table is more complete because you can see hydrogen here. The upper number is the number of protons it has. It's also the number on the periodic table. So when you say hydrogen is number 1, you automatically know it has 1 proton. Okay, so anything you see here, copper, Cu, is number 29 in the periodic table, so you know it has 29 protons. All right, so let's look at the next topic here. So let's actually look at the mass number, right? So the mass number is the number of protons and neutrons. Generally, we say that there are the same number of neutrons as protons in an atom. Electrons, right, I said this already, it doesn't have any mass. It weighs about 1/2000th of a proton, so tiny, no mass. Nitrogen is atomic number 4. How many protons does it have? Well, its atomic number is 4, so you know it has 4 protons. How much do you think it weighs? Well, we assume that the protons and neutrons are the same. So if it has 4 protons, it also has 4 neutrons. 4 plus 4 is 8, so it weighs 8 atomic mass units. If we go to nitrogen is 4. Oh, you know that question was wrong. I need to change that. Beryllium is 4. Nitrogen is 7. I was like, what's going on? Beryllium is 4. Okay. Anyways, let's move on. So let's look at the next topic, the isotope. So an isotope is different weights of an atom. What accounts for the different weights? Well, we know that neutrons and protons create the weight of an atom. So an isotope is going to be the same atom, but different weights. So what's going to be the difference in the heaviness of an atom? It's going to have to be the number of neutrons, right? So if the proton has to be the same, so I fixed beryllium here, now it's beryllium. If the number of protons is the same, right, it has to be the same because you're going to change the element if you change the number of protons. Then to have a heavier or a lighter atom of that same element, you have to change the number of neutrons. And that's basically the definition of an isotope. An isotope is an atom with the same atom, but with different weights. Let me see if I can find here's my isotopes slide. So here's carbon. There are 3 isotopes of carbon, and isotopes just exist in nature. No one's making these. There's just happens to be some carbons out there with exactly 6 and 6 protons and neutrons that weigh 12. We call it carbon 12. There are some carbon atoms out there with an extra neutron, so it has 6 protons, 7 neutrons, so it has 13, a mass number of 13, right? So we call that carbon 13. And then there's some carbon out there that's 6 protons, 8 neutrons, and we call that carbon 14. So they have the same, everything else is the same. The electrons is the same, protons is the same. It's just the number of neutrons that are different. And so they are just heavier forms of that same atom. So that's the word isotope. Isotope is the heavier or different weights of the same atom. So now if we go back to the periodic table, sorry, this is a little bit out of order. This is why, let's take carbon, right? Carbon, the atomic number is 6. The mass is 12.011. So if we were just doing the simple math and just did 6 protons, 6 neutrons, then our atomic mass would be 12, and that would be it. But in fact, the periodic table says the mass is 12.011. This is because of those isotopes. Because there exists carbon 13 and carbon 14, and if you weigh carbon kind of all together, you're going to have some of those isotopes with the carbons, so it's going to be a little heavier than carbon 12, right? Carbon 12.011, so that's the average weight of your carbons. If you look at beryllium, so back to that example, right? Beryllium is the atomic number 4. How much do you think it weighs? We said 8, right? Because it has 4 protons and 4 neutrons. In fact, it's 9. Why? Because beryllium has very heavy or heavier isotopes that exist in greater amounts than that beryllium, the normal beryllium. So beryllium usually has extra neutrons in it. That's why the atomic weight is 9. Okay, so let's take one more example. Let's just take nitrogen, right? So nitrogen is 7. If nitrogen had 7 neutrons, then it would weigh 14.0, and that's it. But nitrogen has some isotopes that are heavier, so the average weight is 14.007. So you can see that all the weights are not just a strict number, that there's a decimal point with some numbers after it because we have to account for the average weight because of the isotopes that exist. All right, so let's talk about what people do with these isotopes. Okay, so I'm going to turn to this question first, right? How many neutrons does carbon 14 have? Carbon is number 6 on the periodic table. Pause to think about it. Okay, so if you want the answer, I'll just walk you through it. So carbon 14, it's 6. So if you take 6 away from 14, you have 8 left, right? So it has to have 8 neutrons in order for it to weigh 14, because 6 of that 14 is going to be protons. All right, so radioactive isotopes. For letter C in your outline, I have radioactive isotopes. These are unstable isotopes, so they're the same atom again, but the nucleus decays spontaneously and gives off particles and energy. Sometimes the atom can lose a proton. When this occurs, the atom changes, of course, right? Isotopes can emit different things. So basically, there's a form of carbon that there's just a little bit more energy in the nucleus that the atom likes. And as a general rule, everything in nature, molecules, everything likes to be at a low energy state. Nothing likes to have extra energy. So they always try and get rid of that extra energy. So if your nucleus is unstable and has a little bit extra energy, you just emit that energy out until you reach a lower energy state. So when you have radioactive isotopes, these are isotopes that are unstable. They're constantly emitting energy. And these energy forms can be gamma rays or beta particles, or alpha particles, or positrons. You don't need to know what these are, but just know that they are constantly emitting some kind of energy. So how do we use this? So there's a scan called a PET scan. So it's PET scan stands for positron emission tomography. And positrons are one of these particles that are emitted from an unstable isotope. So what happens is that you can take this radioactive isotope, you can attach it to a sugar, like a glucose molecule, and so now you have a radioactive sugar. If someone were to eat this radioactive sugar, the sugar goes all through the body, and only the cells that use that sugar, that start to break it down, will emit the energy of that radioactivity. So once you break down the sugar releases that energy. So you can use this to pick up very, very metabolically active areas of the body. Those are called hotspots. Hotspots are high metabolic activity. So if a cell is working really, really hard, then it's going to use a lot of sugar and it's going to emit a lot of radioactivity. So if you scan the body, you can look for these things. So this is one example. So this is a PET scan of two brains. One is a normal brain, this one, and one has Alzheimer's. And the white is very, very hot. Red and orange are very hot spots, very active. The yellow as well, and then the black and blue are not active. So you can see in a normal brain, the normal brain is always very active. It uses a lot of sugar, a lot of calories for thinking. And in an Alzheimer's brain, you can see that areas of normal activity, like over here, are dark, right? It's dark. So we can see that the activity has changed, and you can also see the pattern of the activity where it has changed in the areas of the brain. So this is a useful, use, I guess, for using our radioactive isotopes. Here's another example. So cancer is a very metabolically active mass of cells. The cells are constantly eating sugar. They're hungry because they're always growing. And you can use a PET scan to look for an unusual hotspot in a person's body. So this is only on one side. The other lung doesn't have it, so this looks like a tumor. So I just want to show you a couple of examples of isotopes, radioactive isotopes, and what you can do with them in PET scans. Okay, so let's move on to ions. If you had an electrically neutral atom, what two subatomic particles would have to be equal? So if you're neutral, right, remember the protons have a positive charge, electrons have a negative charge, so they have to be neutral. So protons, electrons have to be equal in order for an atom to be neutral. Hopefully that makes sense. So what if they were not equal? So what if chlorine here, so here's a chlorine atom and here's a sodium atom. Sodium has this one little guy, this electron on the outer ring, and it is lost to chlorine. So chlorine's going to steal that guy, and we'll talk about this in ionic bonds. When chlorine gets an extra electron, what happens? Now we have 18 electrons. Now we have a charge of -1, right? Because we just got an extra negative charge. So we have this whole chlorine ion has a -1 charge. What happened to sodium? So sodium lost a negative, right? So it ended up with an overall positive. It started off neutral, but if it loses a negative charge, we end up with a +1. So we call these charged atoms ions, and we have special names. If an ion is negative, it's called an anion. If an ion is positive, it's called a cation. Just think about how people love cats or love cat videos, right? So you're very positive feeling towards cat ions. All right, so before we move on to the shell model and bonding, I just want to go back here and take a look at what we're made of. So elements that create us, right? So out of all 92 naturally occurring elements, we need about 25 to make our bodies up. 96% of our mass is made of only 4 elements. Which ones? So let's take a look at our picture. So for human beings and most organically based organisms, we're all organically based, but it's oxygen, carbon, hydrogen, and nitrogen. So I like to put this word together, CHON, chon, or you can even go notch, whatever, to remember these 4. Carbon, hydrogen, oxygen, nitrogen, chon. And then what else is our body made of, right? So in our foot, this yellow area gives us some other very important elements that make up our body: calcium, phosphorus, potassium, sulfur, sodium, chlorine, magnesium. And then there's a very small amount in our body that are under this category of trace elements. So trace elements are less than 0.01% of our body, but they're very important. You need everything here in order to function. Even though you need them in very small amounts, they're very important. So what trace elements means that there's a very small amount present, right? So if you watch a crime show, for example, and it says, oh, we found a trace amount of blood on the person's clothing, that tells you it's a very small amount. So for our bodies, usually we get all of our nutrients from the food we eat, of course, and trace elements are usually minerals. So let's take a look, right? So boron, cobalt, copper, fluorine, iodine, iron. These are usually metals, and you find these usually in vegetables and fruits, plant foods. Not to say they're not in animals, but in larger quantities. So iron, for example, is really important for your red blood cells to carry oxygen around. And foods that are high in iron are your green leafy vegetables like kale and spinach. Iodine is really important. Iodine is found in the soil as well. So here are foods that are high in iodine. Milk and also eggs are high in iodine. And this is a picture of the importance of iodine. So even though you need very, very small amounts of iodine, if you don't get enough of it, this can happen to your thyroid gland. This is called a goiter. This is a very large thyroid gland, because this gland needs iodine to make its hormones. And if you don't give it iodine, it swells up because your body is basically asking it to make more iodine, make the hormone, and it can't. But that pressure to make the hormone from the rest of your body makes it grow. So this is the reason actually why when you buy salt, if you look at the label, it says iodized salt. Salt doesn't naturally have iodine in it. Sea salt might. I'm not sure how much iodine has, but this is the reason why the government put iodine in salt, because for a while in the United States, there were a lot of goiters in the Midwest. And it was because people were not getting a diet rich enough in iodine. So the government decided to put iodine in the salt. And that way, anytime a person used salt in their food, they would also get iodine. So it's kind of like a little supplement to the salt. So this is just a opinion that I usually ask the class, and you can just think about this for yourself. I don't need to know. But do you think that adding trace elements to food items is good public policy, right? So do you think that this is a good idea? And then, like you can see, like vitamin D is added to a lot of milks. Is it a good idea or not? So it's something to think about. No right or wrong answers. It's an opinion. And let's move on. So we talked about isotopes. We talked about ions. Now let's move on here. Let's fill out this little questionnaire. So by definition, all atoms of carbon have exactly 6 blank, but the number of blank varies from one isotope to another. So the first blank should be protons, and the second blank should be neutrons. As two atoms approach each other, which subatomic particles are the first to come into contact? So if you visualize two atoms coming together, the subatomic particles that first come into contact, those are going to be the electrons, because the electrons are hovering in those orbital clouds, right? What 4 elements are most abundant in your body? Remember Chon. You can figure that out. A neutral calcium atom loses 2 electrons. What charge does it have now? Is this a cation or an anion? Right, so calcium loses 2 electrons, so 2 negative charges are gone. It's going to end up with positive 2, right? It has a positive 2 charge. Is positive 2 a cation or anion? Remember positive cats, it's a cation. Neon has the atomic number 10. What would you guess the mass to be? Around, right? We're estimating. If the number is 10, you're going to go ahead and add 10 neutrons to that and make it 20. All right, let's talk about bonding. I'm going to pause it here. We can talk about bonding in the next segment.